Okay, so hey guys, this is the videos for tutorial 5. The first problem in here is going into a little bit about influence lines. We're just wrapping that up. This is what you did your lab on. This is what you did one of your homework problems on in the past. And from there, or actually no, this is the first homework problem you have. I forgot, yeah, because we didn't have this on the exam. But you'll have, you'll have influence lines. And then we're going to go briefly over moment area. For this first video, I'm just going to go over influence lines. Get just a brief recap. So recall that for influence lines, we can basically, for influence lines, we're trying to find, we're looking at a single point on our graph. So let's say at this point, and I'm trying to see what happens as I move a load across this beam. So for example, if I'm interested in the shear at this point, what is the shear as I have a point load move across the entire thing? So normally I have a load at a single point, and I'm interested in finding the shear at all points in the beam due to that load. In this case, I'm interested in the shear at a single point due to a load at any point on the structure. This is primarily useful for bridges, where you're interested in, for example, like groups of cars, and due to traffic flow problems, you might have seen this little bit of intro to transportation engineering, but for example, you could have a scenario on a bridge where maybe the critical case is when you have a small group of cars here and a small group of cars here. For example, so like finding influence lines would allow you to identify what load cases would give you the largest value at a specific point. To actually solve for influence lines, I'm going to be using the Moeller-Breslau approach here. Moeller-Breslau just says that we can if we treat our beam physically, if we force it to obey the initial boundary conditions and force the individual elements to remain rigid, we can get the shape of our influence lines diagram by just applying unit rotations and unit deflections. So what do I mean by that? Let's say I'm interested in the reaction at this point. If I wanted to generate my influence line diagram, all I would have to do is take this point, lift it up by 1. This section has to remain rigid, so I'm literally lifting this beam up by 1 at this point. I'm rotating it about this point because I have to maintain my original boundary conditions. This is a boundary condition, right? A reaction is a boundary condition. And this is my unit influence line diagram for the reaction at this point. All right, so if I want to find the reaction, I lift the reaction I'm interested in up by 1. It doesn't matter if it's at the end or if it's in the middle. For example, if I have a cantilever, I want to find the influence line diagram for this. I raise this point up by 1, and I just draw this. This is my diagram now. I've literally just raised this point up by 1. The boundary condition that I had to obey was that I have no rotation. This has to maintain a 90-degree angle. Therefore, I just end up with a rectangular diagram for the reaction at this point. And that makes sense, right? If I have a cantilever, it doesn't matter where my load is. My load can be anywhere in this thing. My reaction is always going to be the same. Right? I could have P here, I could have P here, I could have P at the very end, I could have P near the beginning. My vertical reaction at this point will always be equal to just P. That's for reactions. The next one I'm going to go over is moment. For moment, I take my original drawing, and then I just apply a unit rotation at the point I'm interested in. So let's say I'm interested in this point. I apply a unit rotation there. We'll go over what this angle means in a sec, or later on. So if I'm interested in and again, I had to maintain the original boundary conditions. This is a rigid element, this is a rigid element. The angle between these two rigid elements, by rigid I mean it can't bend. The angle between these two rigid elements is 1. If I go back to my simply supported beam here, let's say I'm interested in the moment here, I would apply a unit rotation here. I need to maintain my original boundary conditions. This has to have 0 deflection here, right? For Moeller-Breslau, I'm treating this as a physical system. I bent my beam at the point I was interested in, but the arms, the members on either side of that point that I bent it about is going to be rigid. It's going to be straight. The deflection at this end of the member has to be 0. The deflection at this end of the member has to still be 0. The only way for both those conditions to be true is if I raise this point upwards. So my deflected shape now looks like this. For shear, I have a very, shear is probably the most tricky case. I have a slightly different thing for shear. I'll tell you that again, I'm interested in this point. For shear, I cut the beam at the point that I'm interested in. I connect these two. Oh, sorry, I don't connect these. This has this gap here. I misspoke. This length here, the distance between these 2 points. So I took my original beam, I cut it at the point I was interested in. I'm saying that the point on the left and the point on the right have to be separated by a distance of 1. The second rule for shear diagrams, and this is more of a guideline, is that these 2 lines should be parallel if at all possible. It is not always the case that you can make these 2 parallel, but if you can make them parallel, for example, maybe one side can rotate but the other side cannot, in that case they wouldn't be parallel. But if both sides are free to rotate, then you should try to make them parallel if at all possible. So what do I mean by that? So in this case, for example, I separated this. If this was in the center, right, this is going to be 1/2 and 1/2 here. I'm talking about the heights. The height of this is going to be 1/2 above the horizontal, 1/2 below the horizontal. But these 2 lines are parallel. Let's say that instead of looking at this point, I was interested in this point. How far above and below do I have to go? Do I keep this 1/2 or 1/2? No. Instead, let's pretend that this is 1/4. I'm going to try to keep this parallel with this. This will be 3/4. This will be 1/4. This is why I should try to keep them parallel if at all possible. It will affect your results. I cannot just say that's always going to be 1/2 below and 1/2 above. So those are the 4 main types of, or 3 main things you can find for this. For this video, I'm thinking what I'm going to do is just similar to what I did in office hours today. I'm just going to go over problem 1A for you, and then I'll let you do part B all on your own. So for part A, but I'm not going to do all of the, oh, I guess I should do, yeah, I'll try to do all of these as fast as I can. I'm trying to avoid making long videos, but it's always tricky. I have no idea how people that post these things regularly do videos that are only like 5 minutes long. So for this problem, I'm looking at first the vertical reaction, and I'm just going to draw this here for now. The first thing I want to find is the vertical reaction at A. In this case, I have a cantilever. To find the reaction, I lift this point up by 1, like so. I have to have 0 rotation here, therefore this angle is known. And I just go all the way across to the hinge. The second boundary condition I have to meet is that I have 0 deflection at my roller. At a hinge, I'm free to rotate, right? A hinge can't resist any rotation, so you can have a kink here. I just connect these 2. I do need to label the heights. This is 1. This is a flat line, therefore this is also 1. This was length L on 2, and this was length L on 4. These 2 angles are the same. Therefore this height here is going to be 1/2. Right? This base is half this base. They have the same angle, therefore this height will be half this height. That's vertical reaction at A. The vertical reaction at B, quite similar. I'm just lifting this point up by 1. I have to pass through the hinge, right? But I can have free rotation here. Let's look back at this member. Can this member rotate at all? I have this cantilever here. The cantilever prevents any kind of rotation. Therefore, this member will remain rigid. It will remain flat. It cannot bend. It cannot move up or down. Because of that, the hinge cannot move up or down. The hinge does allow rotation. Therefore, I end up with something like that. I should not have marked that angle, but this is 1. And again, this is going to be 3/2. And you can use a little bit of geometry to figure this one out. The moment at A. In this case, when I'm working with a cantilever, I can pretend that I have a little arm that's buried within the cantilever. And I'm bending A with respect to that arm. So you can see that I'm bending A with an angle of 1. The other boundary condition that I know I have to have is 0 deflection at this point. Therefore, I'm going to go straight down to the hinge. At the hinge, I'm free to rotate again. Therefore, I just go straight up. This value here was 1. This value here was L on, or sorry, this length here was L on 2. This length was L on 2. This height, this value 1 just represents the ratio of the opposite to adjacent. If I have 1, that means I have a 1-to-1 ratio. That means the height is L on 2. I have L on 2, L on 2, therefore this angle is also 1. This angle is also 1. I have L on 4, L on 4. So these are the two things that I needed to label on this diagram in order to get full credit. My shear at B. Notice that it's saying the left side. The reason why it's it's specifying the left side because I have a reaction at B. I need to assign that reaction to either the left side or the right side, and that will affect my boundary conditions. So what do I mean by that? And in this case, you only needed one of these, but I'm going to show you both of them. Let's look at this. Minus sign means VB to the left. If I look at just to the left-hand side, if I cut it here, I have one rigid element here, and I have one rigid element here. This element here has to have 0 deflection here because it's connected to the roller. The only way for me to still find the shear value for draw a line that's separated by 1 is if I lower the other side by 1. And it doesn't matter whether I lower or raise this side by 1. The only thing that matters is the magnitudes. So I could have all these flipped upside down and the diagrams would still be correct. This height here is going to be 1. I have no rotation here. Therefore the hinge can't move up or down, but it can rotate. I go through this point, and again I had to make this one parallel with this one. The two arms on either side of my shear cut have to be parallel, if at all possible. I end up with something like that. The height here is 1. The height here, these two angles are the same. Therefore the height here is 1/2. If I look at VB on the right side, I would see that I would cut this here. This would have 0 deflection, therefore this has to go down to this point. This hinge cannot move up or down, this point cannot move up or down, therefore this one cannot rotate anymore. So even though the hinge is free to rotate, I have 0 rotation here. And I end up with a shear diagram that looks like this. So you can see that these two are very different just by changing the location where I took my cut. The last one is the shear at X. And in this case it doesn't matter, X is the hinge. I don't need to look at left or right, it will have the same result either way. I'm cutting it here. This one cannot rotate, therefore this deflection will remain 0. I'm going to lift this point up by 1. It's going to pass through this point, and I'm going to get a diagram that looks something like this. So you can see here this is 1, and again this will be 1/2. I'll have 0 here, and this is one of those cases where they will not be parallel. So it is, if it's possible, they should be parallel. In this case, it's not possible, therefore we're not drawing them parallel. And that's over for this one. Let me know if you have any other questions.